So SR-IOV seems like a pretty good deal. The high-powered NIC is already doing the sort into queues, so we can cut the hypervisor, including the virtual switch, out of the transfer entirely. Fewer people handling the information means faster transfer of information. There are two things that we need to look at when turning this feature on. First is whether or not the hardware supports it, and second is finding that on switch. From a hardware standpoint, there are two things that need to support I/O virtualization for this to work: the network card and the motherboard. And it's easy enough to check the specifications of a network card before you buy it. Here I have Intel's website and, as of this recording, a current list of the network adapters that support this feature. And you can look at the specs of any network card that you're considering purchasing or have already acquired. Again, for example, on Intel's website, if I scroll down on the specs, I do find that this NIC is SR-IOV capable. Coincidentally, it also supports virtual machine queuing. But just to give you some perspective on the class of network adapter we're looking at, again, as of this recording, Intel values this card at just under $400. Finding the right motherboard may be a little bit of a different story. I would caution you to look beyond the specs of a chipset and confirm that the actual motherboard and BIOS support the feature that we're looking for. Sometimes a chipset is built from Intel or from whoever to support a technology, but then that chipset is applied to a motherboard that is not. For continuity's sake, here we are again on Intel's website looking at SR-IOV support on Intel server boards, and we have a handful of boards that are listed. Again, if I look at the specs for a specific board, and I scroll down to look at some of the available advanced technologies, there is the virtualization technology for I/O. And if I were to click on the question mark for clarification, it does talk about I/O virtualization. This is the support that we would need in a motherboard. The next layer of compatibility that we need to be concerned about is whether or not our guest environment is going to support SR-IOV. And within Microsoft Server Hyper-V, you can have guest operating systems of any 64-bit workstation, Windows 8 or newer, any 64-bit Windows Server, Windows 2012 or newer, and sorry, that's it. Those are the only guest environments that are actually supported by Microsoft's Hyper-V. The hypervisor needs to have a more direct link between the assigned memory space and how the guest operating system is going to use it, and a Windows host to a Windows guest is going to be able to more completely establish that link. Now, this feature will work on both first-generation and second-generation Hyper-V virtual machines, but there are an increasing number of technologies that won't, so it's a good idea to start getting used to creating as many of your virtual machines as second-gen as you can from this point forward. So if I've met the requirements, we can start to turn this service on. The first step is to turn on I/O virtualization in the BIOS. And different manufacturers will put this in different places in the BIOS. Some will put it under advanced features, some will put it with the definitions of the onboard hardware. On our server, HP placed it under the Security tab inside the System Security under the Utilities heading. And here you can see the second item on the list is Intel's I/O virtualization option, and it has to be enabled. And if at all possible, you should turn that on before you install the operating system of the host server. This helps ensure that when the NIC drivers and the chipset drivers install, everything will fall into place. A second best approach is to go in and update your NIC drivers and update your chipset drivers after you enable that feature in BIOS, so that those drivers will be installed with that support enabled. And the next step is done from right here inside Windows, or more specifically from the Hyper-V Manager. And we're going to see the importance of planning this first rather than trying to update it later. We're going to take a look at the virtual switches that we already have configured. And if I were to look at the details of the virtual switch that I have created, I'll see down at the bottom a note that says SR-IOV can only be configured when the switch is created. I can't take an existing switch and enable SR-IOV. That's a decision that has to be made when the virtual switch is created. Now, fortunately, creating a new virtual switch is not a difficult thing to do. I can select New Virtual Switch and specify that this is a switch that will connect directly to the outside world. And as I create the switch, I can go through the process of assigning it a name, selecting a physical connection that it will use to reach the outside world. Side note here, you have to choose an adapter that's not already assigned to a different virtual switch. And then you can check the box to enable single root I/O virtualization. Now, when I go ahead and apply these changes, since I'm doing this through a remote desktop connection to the server, I should expect there to be a slight disruption in network connectivity. This is normal, and we've seen it before when making configuration changes to virtual switches. So I'll go ahead and say yes, and if my screen blinks through black for a second, it's expected, it's no big deal. And now we're almost done. Now we just need to enable it for the specific virtual machines. So as I close this, I can go to the settings of a specific server, and now under the network adapter and hardware acceleration, we're now back to a screen that we've seen before. Now I can check the box to enable single root I/O virtualization, and now that everything is in place, I can apply these changes, close this box, and now I/O virtualization is in place for this virtual guest on this virtual machine host running on the motherboard and NIC that we carefully selected. In the last video, we looked at one type of encapsulation that can help us create a software-defined network that is not bound by traditional limitations of routers. While Layer 3 is an important part of how network traffic is isolated or forwarded, it's not the only layer. Most switches rely on Layer 2 information to direct traffic within routing domains. This creates another opportunity for an SDN component. Most operating systems and NIC drivers use ARP to resolve a destination IP address to a destination or next hop MAC address. Layer 2 devices can then forward a packet based on that MAC address. Switches and other forwarding devices have 3 different ways to determine where a MAC address is located so the packet is forwarded in the right direction. The first, and the least efficient, is for the device to learn for itself and create its own internal ARP table. This creates a lot of broadcast traffic as the switch tries to learn the network and verify things every time they change. The other 2 methods require some kind of centralized directory. The directory can be queried by the forwarding device, or the central directory can publish to the devices. Having the switches look up ARP values from a central list saves a little bit on broadcast traffic, but it still requires a switch to check in every time a new node is found or when a packet is undeliverable because the node is moved. For these reasons, Microsoft implemented virtual extensible LANs to use this third model and maintain the ARP table in the network controller role so that it can be published to the switches as changes occur. This way, the switches have an ARP table that always has the most current information. Just as GRE wrapped a new IP header around the intended destination, Virtual Extensible LAN adds a new Layer 2 header with the destination MAC address of the virtual machine host. This allows the virtual switch and each virtual machine inside the host to have their own Layer 2 identity, while allowing physical network fabric to efficiently deliver the packets. Implementing this kind of control is a bit more involved than simply opening a GRE tunnel. You have to write your own switch extensions that you're going to bind to the driver stack. Microsoft intends for these NDIS filters to be written by experienced developers, and I'm showing here the MSDN page that gives a good introduction to how to go about doing that. But for our purposes here, I do want to show you the architecture of how Windows Server 2016 uses these extensions. For starters, the protocol standards for VXLAN have been in place for a while. Many manufacturers of network hardware have already been using them. So not only did Microsoft not have to start from scratch, but they were able to apply widely used standards to ensure that this would work on a wide range of hardware. Next, all three types of virtual switches in Windows Server Hyper-V support these switch extensions. Whether you are using an external virtual switch that maps one physical adapter to the internal virtual adapter, or an internal virtual switch that only connects the virtual machine host to the virtual network, or even the private virtual switch, which only allows traffic to be exchanged between virtual machines. These extensions are written to provide specific filtering and to identify the network controller that will publish the updates to the ARP list. Some software vendors that write applications for SDN environments may require some specific filtering, and they will often publish INF files that can be installed to provide their specific extension needs. Now, I opened this segment by discussing the need for help forwarding packets. Extensions can also be created to filter traffic or even capture traffic based on Layer 2 information. These extensions could be used to implement network monitoring or to eliminate the need to ever use VLANs again. Here's the end result of an extension for MAC filtering and forwarding. Say Virtual Server 2 on physical host A creates a network packet that needs to be sent to Virtual Server 3 on the right. The destination MAC address is the MAC address of the Virtual Server 3. We've talked about the flexibility of virtual networks. Virtual Server 3 could be on a different physical host than it was yesterday, but today it's on physical host B. The extensions on the virtual switch in host A can look up the MAC address for physical host B from the most recent list published by the network controller. So a VXLAN wrapper is placed around the original Layer 2 headers, and a new Layer 2 header is added around that. This allows the frame to be delivered to the right physical host, where the VXLAN wrapper is removed, so the Hyper-V switch can deliver the original frame to the NIC with the original destination MAC address. All of this processing creates a little bit of work both up and down the SDN stack, as well as across hosts. The next part of this chapter looks into load balancing that traffic. RAS gateways support three different types of tunnels. L3 and GRE tunnels are very efficient, but provide no built-in encryption. There is one other type of VPN or tunnel supported by RAS Gateway in the Network Controller role, or the Windows Server Gateway and System Center, and that is Internet Key Exchange, or IKE version 2. Now, IKE version 2 is a VPN protocol developed in a joint venture between Microsoft and Cisco. It was initially a popular protocol for BlackBerry and other mobile providers because it did two things. One, it had decent encryption and security, and two, it was tolerant of flaky network connections. Just as we understand that a mobile device is prone to bad network connections, we also expect that a glitch in the line will occur in any internet connection from time to time. IKE version 2 is designed to maintain a connection so these common anomalies won't completely destroy a network conversation. When creating a site-to-site VPN between locations, IKE version 2 is a preferred protocol for just that reason. It can keep the line open in the event of short hiccups, so connection-oriented protocols like TCP can do their job to ensure delivery of all messages. RAS Gateway in Windows Server 2016 can create an IKE version 2 tunnel between an office network and a segment of virtual servers in a data center. This kind of gateway allows you even more flexibility in where you place the subnet of virtual servers. That segment could leave your site and move to a public cloud provider. It could even move from one public cloud provider to another. This segment of your network is completely decoupled from the physical network. This RAS gateway can be directed to the new location in such a way that the devices on your home network don't even have to know where they are. They don't even have to care. Now, this type of gateway has been described in courses on remote access and other chapters on various VPN technologies, But this RAS gateway is part of a software-defined network. If you install the network controller role in your network, or choose System Center as your network controller, you can manage these gateways as an integral part of your entire network fabric. Like the GRE tunnel, it also requires the remote access role to be installed on the edge server. But the flexibility of this tunnel allows the edge server to be a virtual machine, if that's the way it fits in your topology. And whether it's a conventional VPN, accessible to a wide range of devices, or direct access, which is seamless for enterprise Windows clients, but nobody else, the concepts behind a RAS tunnel and standard routing and remote access features appear the same. The primary difference is that RAS gateways work with a network controller and can be more easily updated as segments move. One other difference, and this is for those of us that like the desktop tools, the RAS gateways cannot be created in the GUI tools. PowerShell is required. And I showed several of these PowerShell commandlets in the GRE video in the last chapter. We used add VPN site-to-site interface to create the GRE tunnel. The same command and several of the same parameters are used with different options to create these more secure IKE version 2 tunnels. And if SDN compatibility is the reason you're going with RAS Gateway rather than a traditional site-to-site VPN, remember that Windows Server anticipates an SDN data center will be running on a high-performance network. It's not that they can't run on slower networks, but keep in mind that the controller does create some new traffic, and all of these technologies are designed to combat the issues that are found in high-use environments. It's most often seen in public clouds, where the cloud provider is using multiple servers for a single client or a single server for multiple clients. In this multiple tenancy environment, the need to scale individual clients quickly is important, as is the ability to migrate one client's virtual servers from one host to another or from one location to another.